Hey everybody, welcome to something brand new. This is product integrals, specifically geometric integrals. I'll go into the details about that a little, basically in a couple minutes. First I want to say I'm a little sick right now, so if I do sound different, that's why. And I probably will sound the same way in the next few videos, since I record my videos I record a few videos at a time basically. So it's alright, I'm okay, don't worry about it. But yeah, so basically, before we get started, you should know what a regular integral is in standard calculus. You should also know what the sum is. I feel like you probably learned this before the integral, but you should definitely know what this is. And this is the third thing you should know: the product, which is basically the multiplicative version of this. I've made a few videos on calculus, but if you're not familiar with this, you should go to Khan Academy or something. The sum, I feel like a lot of people know. It's just, if you don't, then there are probably some videos on YouTube talking about it. This, I've definitely made a couple videos using the pi product. Basically, it's just the multiplicative version of the sum, the sigma. So yeah, basically, if you know all three of those, you should be good for this video. You also should know the connection between the sum and the product. I made a video on that about a month or two ago. You should also, yeah, that's pretty much it. You should know about the definition of what an integral is, stuff like that. Just be comfortable and well versed in those things, because if not, then you probably won't be able to follow much in this video. But anyway, with that out of the way, I do want to use this video to introduce you to product integrals. I'm not going to go through an example in this video, it's just we won't have time. I'll do that in the next video, which will come maybe in about a month or so. But yeah, there are three types of product integrals. That's why I have geometric in parentheses. Geometric is type 2 in this Wikipedia article, which I will have linked in the description, so you can get more information on what it is and what its uses are and all that kind of stuff. Basically, this in my opinion is the best because it's very synonymous with how the additive integral is, the normal integral we study. And yeah, it's a very cool thing because it's not very common to see. You don't really learn about it. You actually don't learn about it at all in standard calculus. And I don't really see it anywhere else. So it's kind of rare to come across, but it's something that's very cool and it's very easy to understand if you know these three things. But basically, yeah, again, I just want to use this video to introduce you to the topic, help you understand how you can find one, and yeah, I'll leave you off with a little homework assignment at the end. So yeah, I guess we can just get started. Alright, so behind me you can see this table here. I copied this straight from the Wikipedia article. Basically, it highlights the differences between all four operations that we're going to be using today. So first, I'm going to start with discrete additive. Basically, this is your sum, your discrete sum, using the sigma notation from A to B. This is like f of 1 plus f of 2 plus f of 3 all the way to f of n, and, just something like that. And then the continuous version of that is the integral. You go from A to B of f of x dx. The difference between these two is that this is, you have defined intervals basically between, so this is like f of 1 plus f of 2 versus this is like f of 1 plus f of 1.000001. And again, you can't quantify it, it's just such a small amount, it's basically 0. So you're adding up little tiny, very, very, very tiny slivers of a function and basically adding those up. Here you're adding defined intervals. So that's the difference. That's what discrete means. Discrete is chunks that you can see, versus continuous is little things that you basically just can't see. Multiplicative, we have our product, and this is basically the multiplicative version of the sum. You're just so this would be f of 1 plus f of 2. This is f of 1 times f of 2 all the way to multiplying to f of n, or in this case f of a times f of a plus 1 plus times f of a plus 2 all the way to f of b. That's basically what that means. And this is what we're going to be learning today. This should be completely new to you. You probably should have already known these three, but this one is new. This is the geometric integral. This is what we're going to be studying today. This is one of three types of product integrals, and I like this the best because it's very like analogous to everything else. So this is the multiplicative integral, the geometric integral from a to b of f of x, not times dx, but to the power of dx, and that's what makes this different from this one. So yeah, that's basically the differences between the two. So yeah, let's continue to see how we can figure them out. Alright, so let's continue. Basically, here are the definitions of our integrals. So this should be you should understand this. We don't really need the bounds here, it's just kind of, you don't really need it. But basically, this is the definition of our additive integral, while this is the definition of our product integrals. You can see that they're very, very similar. This is just taking delta x as it goes to 0, and then just summing up all of the f of x's times the delta x. Here, very similar. The only difference is, of course, here's pi, and then here is the delta x in the exponent instead of in the as a like being multiplied. So let's use the connection between the sum and the product to figure out what we're going to put as like how to connect the sum with the product integral. All right. So the connection between the sum and the product you should be familiar with. I've already made a few videos on this. It's equal to, or it's not equal to, it's the natural log. Okay, and I could use any logarithm, but the natural log is the easiest to work with in calculus in general, so we're just going to be using that it's going to be a big parentheses because we have the product, and I'm not going to put bounds here, but you can think of this as from A to B if you want, but it's really not necessary, it's just kind of confusing. I'll put the index though, it's I as our index of f of x sub I. Alright, so what this means is we take the product of a bunch of functions indexed at I. Actually, I'm sorry, this should be f sub I of x. It means slightly different things. I was getting confused with this. This means that you're taking the same function, putting in different inputs. Here we're talking about different functions with the same input. The input here for the x isn't really necessary. You could just be talking about multiplying numbers, but since it's calculus, we deal with functions a lot, so it's very common to like think of functions. But again, it's really not necessary. The x kind of just is, it's just there, you know. So the natural log of a product of functions, this is equal to the sum. Oh my god, that was terrible. I'm sorry. Here, let me. There we go. That's a lot better. The sum indexed with the same index, because we're talking about the same numbers here, and we're taking the natural log of our functions. All right. So I hope this makes sense to you. If it doesn't, then watch my video on the connection between the sum and the product. But if you think about it, you probably know from algebra that natural log of a times b is equal to natural log of a plus natural log of b. That's what this is reflecting, but just in more mathematical terms and more generalized stuff, right? So now if we want to isolate this, so let's just isolate this. Let me make that bigger, actually. Let me make it less skinny like that. Okay. All right. So again, we're having our index I of our f sub I of x, right? Okay. And since we have to take the inverse of this to get rid of our natural log. Inverse of natural log of x is e to the x. So we're going to be doing e to the sum. So this whole side over here. And this is the discrete version. This is what we've already found in a few videos, and I've actually used this identity in a couple of videos in the past, and I think I'm going to upload another video with using this identity in about like 2 weeks or so. So this is a very, very important identity. I love it so much. It's very applicable in so many different things, and it's super cool. So the product of functions is equal to e to the sum of the natural log of the function. So I think it's a little slanted, yeah it is, but it's okay. So what does this tell us? Well, it talks about the discrete version, but how about the continuous? Well, it's actually really not that hard to go from the discrete to the continuous, because really it's just thinking about it in terms of different like intervals. Here we're talking, in the discrete we're talking about like, oh, we have specified intervals, like intervals of 1, you know? But here, all you're doing is just saying, okay, those intervals are now a lot smaller. That's the only difference. So we really can just replace everything, all these discrete things, with the continuous version. So let me try to not make this too slanted. So this just turns into this. And yes, we don't have a delta x, but you can think of having a delta x and it approaching 0 basically. I'm just doing this in a very quick, not too like mathematically correct way, but it is still a way to get there. And this is actually the formal definition of how we can phrase the continuous product integral in terms of the continuous additive integral. So let's do it. So we're gonna go the pi from a to b of basically we're just gonna copy paste this. We get f of x to the to the dx. And it's kind of weird saying to the dx, but yes, it is to the dx. This is simply equal to e to the sum, the integral from a to b of f of x times dx. And now this is the fascinating connection between the sum and the product, just in terms of continuous functions. And that's very slanted, so let me just fix that quickly. And so I don't think I specified, I think I forgot to put the natural log here whenever I did that, so I just corrected that, and I put a box around that because that is the major result of this video, and that is how we're going to find our product integrals. So, for your homework, I can actually give you some homework here. Where did my marker go? It's over here. So, for the homework that I'm going to give you guys, I'll just put it over here. You can make its own little section for that. Your homework is going to be to find the product integral, the geometric integral that we found here, from a. Actually, no, not from a to b. You don't need to do it from a to b. Just the general, like if you're doing like an indefinite integral, this is kind of the same thing. Of x squared, and this is to the dx power. So I want you to try to find this. Definitely use this this result that we found to do that, because if not, then how else would you do it? But basically you would do e to the integral of the natural log of x squared dx. That's a major hint, and I think you should be able to do it. So I hope you enjoyed, and thank you for watching, and I'll see you in the next video. Bye guys.